All right, thank you so much, and thank you so much for the organizers for inviting me. Actually, so the truth is, when I first got the email from the organizers, it was on January 9th, because I went and checked, and inviting me to come and give a lecture, I really thought it was a joke, that it was a mistake. I don't work with rheology, I don't work with large-scale simulations, so it's such an honor and privilege to be here. And maybe the organizers have realized that it was a mistake, but it's too late now because I'm here. So yeah, hopefully we'll make the best out of it. As Herbert already gave away the punchline of the talk, it's going to be about particles and interfacial instability. And hopefully I'll be able to wrap this up pretty quickly. And I don't know if I'm able to break the rules here, but if you don't mind asking me questions during the talk, is that allowed by the organizers? Okay, because that actually helps me calm down and maybe be able to engage with the audience is a very nice thing for me. So please feel free to ask me, especially clarifying questions. So I like to start by thanking the people who did the work, and I guess everybody does this, right? So I have 4 students, or 4 people in my group right now who's doing a lot of the work, but the topic today was mostly done by Fong and Jungchul. See, I am not very coordinated, okay. Who are not in my group anymore, but most of the experiments and the analysis that we did were done by these 2. And if there's any time remaining, I might talk about a little bit about what Ben and Navid are currently working on or wrapping up in lab right now, so we'll see. But it's a small group, so everyone works together, so you'll see everyone's face will pop up here and there. Okay, so broadly speaking, I like to study dynamics of fluid-fluid interfaces in different scenarios, so I can just show you a little bit of what I'm working on. So in everything that we do, we like to sort of combine tabletop experiments and simple mathematical modeling. So simple is the key word here, simple. A part of it is that I don't have a lot of funding, so it's out of necessity, but in some ways, I also love the simplicity. I just find it really beautiful. So one of the problems that I'm working on right now with Mike Shelley at Quran is modeling and doing the experiments of how a partially wetting droplet responds to airflow. In this case, there was an extensional flow that's coming down. Another project I'm working on with a friend at Oxford, Chris McMinn, is actually looking at air migration patterns inside this hydrogel packing. I don't know if you can really see, but we see very interesting behavior we're trying to understand right now. That's not quite true. We understand some things, but the paper is still under review. So obviously we don't understand it that well. The reviewers are not very impressed. So we'll see. Next. One of the newer projects that I started with a friend, also collaborator, Xiang Chang, at University of Minnesota, is actually looking at particle assembly on a fluid-fluid interface. And I know a lot of people do this kind of trying to understand, due to capillary interactions, how do particles actually collect together on the interface. But the thing that interested us was that what if we try to actually move the interface? So we're dynamically changing the surface area and the curvature of the interface as the particles are collecting. So that's one of the newer projects that we're starting right now. If any of this you find interesting, I'm really glad. Unfortunately, I'm not going to talk about any of this because we're going to talk about the thing that Herbert said I would talk about, which is, can suspended particles actually induce interfacial instabilities? And of course, the answer to that is yes. So if you don't remember anything from my talk, you can just remember that. So that was kind of a broad question. So it made sense for me to start with maybe the most seminal interfacial instability that you could think of, which is viscous fingering, and I know everyone here knows what it is. Just to give you a really brief overview, so if you have an invading phase or invading fluid that's viscous than a defending phase, then you get this instability, and I know I'm not talking about gravity and other kind of a stabilizing effect right now, just to keep it really simple. So another way of saying this is interface unstable when mu I is less than mu d, or if the ratio between the 2 is greater than 1. So I will, at some point, maybe mention this mobility ratio, so maybe you want to pack that away in your brain somewhere. And of course, as you know, this has been a problem that's been studied by so many people since 1950s, and maybe there was a work by Hill, I think before then even, but it's still being studied by a lot of people, especially, I think there are quite a few. Oh no, I skipped ahead. So this is really hard to work with. Okay, sorry. Let me do this. Oh no. This is being recorded? Oh, great. Okay, all right. So let's fast forward that part. So this is being studied. We understand it very well, but there's a lot of interesting physics you can study out of this. But the place that I wanted to start was actually starting with a completely stable configuration. So I have a very wetting a silicone oil that's much more viscous than air, of course, that's just displacing air radially inside a helical cell. So basically 2 glass plates that are parallel, and we're just filming it from top down. And as far as this experiment is concerned, nothing really happens, which is exciting. And we decided to just put particles inside this oil. And the beauty of this experiment is that if anything happens that's other than this boring experiment, then I can blame it on the particles. That's how my brain works. So this is what we got. So we add particles, and maybe you've seen this video before. Something happens, thank goodness. So you can see there's this particles clustering that was clustering around the interface that's growing perpendicular to the interface right here, and there are deformations on the interface. So this is what we like to call particle-induced viscous fingering, and we've been studying this for a while. The first time that we saw this in lab, and maybe for the first 6 months, I really thought I was the first person to have seen this, and of course that's not true. But I was really happy for 6 months. But I did find a paper in PRL by Tang et al. In 2000 basically showed this effect, but we just decided to go in and just dig into it a little bit more. And hopefully we have something new to contribute. So once you realize that whatever you are seeing is because of particles, it makes perfect logical sense that the more particles you put in, the more effect you're going to see. So as you see, as a function of concentration, the more pronounced the fingers that you see. But one other effect that I didn't necessarily expect was that this was also strongly dependent on the particle size, or to be more strict, or to be a little bit more clear, h over d. So basically the gap size divided by particle diameter, h over d. So the top row is for relatively large h over d. I say it's 10, and I'm hoping to push it towards a continuum limit, if you would humor me. And you see that you still see fingering actually at much higher concentration, and what I'm going to show you later is that the fingering behavior, the dynamics itself looks a little bit different. And down here is a series of experiments I've shown you before that were conducted with the larger plastic particles. Again, forgot to mention that these are plastic particles. There's nothing special about them. They like oil. They're mostly quasi-neutrally buoyant. They're slightly heavier than oil, but during the time scale of the experiment, we believe that settling is not an issue. So if you basically put these 2 sets of experiments next to each other, and really the only difference between the 2 is that this is small h over d and this is large h over d. And you see a lot more pronounced fingering. And even here, though, if you wait long enough, it's a lot more gradual and subtle. You're going to see this fingering forming on the interface. So I will still characterize this as fingering, but we're going to give it a slightly different name so that you know what I'm talking about when I say these things. Sure. Yeah. Oh, yeah, for sure. Right. So constant volume fraction is kept constant between the 2 experiments. So they're both done at 30% volume concentration of particles. Yeah, but you're absolutely right. Any other questions? All right, so the right-hand side with the large particles, I'm going to call this band fingering, and I didn't really point out why I'm calling it that, but hopefully it'll become clear in the next slide. And I'm going to call this weak fingering, kind of an unfortunate name, but you see one is a lot more pronounced than the other. And the reason why I'm calling this a band fingering is that, as you see, before the finger forms, there was a basically circular band of particles on the interface that breaks. So that's why I'm calling it band fingering. So you're going to hear me say things like band formation, band breakup, and this is what I'm referring to. And of course, we can do this kind of qualitative observation all day long, and we've done a lot of experiments of this nature. But at the end of the day, we have to do something a little bit more quantitative. So my poor student Feng did this. So he basically took all the data, and he basically measured the dimensionless basically total deformation of the interface, lambda, small lambda here. So this is how we define it. So basically, when everything is a perfect circle, lambda should be 0. So the larger lambda is, the more deformed you are from a perfect circle. So what we characterize at band fingering is that there is this very distinct peak in lambda. And that happens to correspond to exactly the moment at which, after the band has formed, the band actually breaks. And you can see then lambda goes down because the interface actually tries to recover its circular shape. So if there is any time, I'm going to talk a little bit about that as well. All right. So we've done a bunch of experiments, and we did all the analysis, and we said, all right, let's just put everything on a phase diagram. So we basically said there are two parameters that count. So we said h over d, and there's phi naught. So we organized everything here. And I also have to make sure that I understand what we're looking at is really time dependent, because I know everything is changing as a function of time. It's a radial flow. So when I call something is unstable or stable, I am saying that I see instability within the time frame of our experiments. So I'm acknowledging that we definitely understand there's a time scale issue here, but please stay with me. So there are a number of things that are interesting and maybe confusing, so I'll try to break it down and tell you some of our questions. So one of the things that's interesting is that there seems to be a very specific value of h over d below which we see what we call band fingering. So can we understand this onset? How do we make sense of this? So the colors are not showing up very well, so I don't know if you can see, but there is also this very nonlinear or this very curved shape of boundary of weak fingering. How do we understand that? And the truth is, I don't have all the answers to these questions. So a lot of what I'm going to tell you is more of the questions that we still have, and maybe invite you to maybe help me, or maybe you can go out and find these answers yourself, and I'll be more than happy if people got involved. But before we can even attempt to answer any of those questions, the first thing we have to answer is, what is the basic mechanism of fingering? Why is this happening in the first place? So if you actually are going to understand this basic mechanism and walk away thinking that makes sense, I'll be extremely happy. And I'll be ready to just wrap up the talk right then. All right, so let's just imagine the Hilly-Shaw cell, or not just to forget the fact that it's a radial flow, just take two parallel plates and think about fully developed flow. Everyone here knows that we're going to get this nice parabolic flow profile. And now let us imagine putting particles here. And one key thing that I do want to mention is that I am working with large particles, non-Brownian particles that are actually not governed by Brownian motion. And I think that's an important point, because in that case, what Eckert, Voss, and Layton found back in 1980s is that these particles like to basically preferentially aggregate near the central line, because that's where the shear is basically minimum. At this point, it's going to be by symmetry 0. So if you actually had a free surface instead of a plate, you would actually see particles flow near the top against gravity, because that's where shear is 0. So we understand this. But this actually has a very interesting consequence in this problem, because that just means if you just took average particle velocity across this section, right? This must be, by kinematics, ever so slightly greater than the average mixture velocity, just because there are more particles near the center where flow is faster. So this just makes logical sense. So once you believe this is true, and once you recall the fact that, oh yeah, we actually have an interface that's expanding with a mixture velocity, at some point these particles will have to catch up to the interface and basically accumulate there. So that's what we believe is happening. And if you're not convinced yet, we can do a very simple experiment just to prove our point. Here we purposely injected pure oil ahead of the suspension, and you should be able to see that the particles eventually catch up, because they are moving ever so slightly faster than the average mixture velocity. So once you believe in this mechanism of accumulation, then actually we're done. We have every ingredient that we need to see the effect, the phenomena that we were observing before. First, we have accumulation. Accumulation also means that this would give rise to this destabilizing viscosity gradient within the suspension, right? So we have basically slightly less concentrated suspension invading into a slightly more concentrated suspension. So mu I is less than mu D. So that's a recipe for what we call the miscible viscous fingering, because this gradient is within this boundary, immiscible boundary. But once you form these basically clusters normal to this boundary, if you just have more flow coming in, naturally it's going to deform the interface. So this is at least a scenario that we think corresponds to what we call weak fingering. And we can actually really quantify this particle accumulation as well, because we have this data, right? We can see this, have images of these particles, and by just taking the light intensity data and inverting it basically, and by making sure that everything, all the mass is conserved in the right way, we can actually extract its depth average particle concentration as a function of position for different time. One interesting feature that came out of this that we didn't necessarily look for is that we believe that this depth average concentration is expanding in a self-similar way. I think we understand it a little bit better now, but we're not really ready to share that, I guess, yet, because we didn't really sit down and write it down. But shear induced migration. So interestingly, particles in the z direction migrate towards a center line where the flow is faster. Therefore, the particles move faster in the radial direction. So migration in the z direction is the key. Yeah. No, it's not. So there are two places. So I was just making a point out confusing people. Sorry. Right, so I was trying to make a point that because now we have less viscous fluid, in this case suspension, invading a more viscous fluid, we have a recipe for miscible or viscous fingering. So that's why we see this formation of particle clusters. Yeah.
But the challenge raises, as always, an interesting point. If there was a free surface, then that would be at zero shear and maximum velocity.
Yep.
And so the particle would rise to the surface.
Yeah, actually, so Andrea Bertozzi, who I worked with as a postdoc, she does a lot of these experiments with free surface flows. In her case, though, she's doing it down an incline. So what she sees is that at higher concentration, like you said, particles float on the interface, and they actually move faster, and they reach the free surface or the front faster and accumulate there, and they actually help suppress fingering. So there are cases where having particles destroys fingering, and in this case, it actually helps it. But in her case, if you just have a pure oil going down an incline, it's already unstable. So now adding particles in that scenario is not helping you with fingering, it's actually suppressing it. That's why I thought this was also interesting, because a lot of times when people think about particles and interfaces, they're looking at it as a mechanism of suppressing fingering. But here we said, oh yeah, okay, well, maybe not. We wanted to do something different, so. Any other questions? Am I okay with time? I don't know. That you are in charge of time. Yeah. Okay, sorry. Sorry, it's 2 a.m. or 2 a.m. and 20 minutes in where I was yesterday, so I'm a little bit all over the place. Actually, I'm always like that, but I can use that as an excuse because I am actually jet lagged. Okay. Okay, all right, sounds good. All right, so I'm gonna get going then, all right. But I do want you to remember this. So remember this graph, and remember the fact that from this images like this, we can actually extract what we call particle depth average particle concentration upstream from the interface. So phi bar up is something that's going to show up, and of course, because of this concentration accumulation, this value is less than the particle volume fraction that we inject the system with. So it's less than phi naught. Makes sense? So that's the picture we're drawing for the weak fingering case. So essentially, for band fingering, we actually think it's the same exact thing, right? But really, the only difference is that in one case, you have very sharp particle concentration accumulation. In the other case, you have this very subtle and gradual accumulation. That's why the miscible viscous fingering event, one is very violent and the other is very subtle. But really, when it comes down to it, we really think it's all about particle accumulation. So really, I'm in the wrong session. I shouldn't be in the interface session, but here I am. So really, the question is, why gradual versus sharp particle accumulation? Is there any way we can justify seeing this versus this? So we thought about this for a minute, and now we no longer could ignore what's happening near the interface. I was really trying to stay away from it. But thankfully, though, there are people who have studied what the flow looks like near a moving interface. So there is a flow right near the interface that people call fountain flow. So people have studied this for actually many, many years ago, actually in the context of injection molding. So I could basically take from this literature that basically says if you're actually moving with this interface, you actually have to think about the fact that if you're far away from the interface, you're a parabolic flow profile, right? You're fully developed. If you're at the interface, then you're supposed to be a plug flow. So there must be some transition between the two that accounts for this difference. And that secondary flow is what people call the fountain flow. So of course, this is going to be going to break down if there's a wetting film, and there's a lot more complicated stuff that happens right there. But this is a basic picture you can draw if you're a little bit far from the interface, but close enough that you can capture this effect. And you can write down the stream function. So we adopted what Carnes has already written back in 1970s. And we basically said, is there an interesting length scale that we can get out of this fountain flow? And what we're looking for was basically the distance from the plate that tells us where the flow basically goes the other direction. So if you could imagine a particle that's coming and trying to accumulate in the interface, maybe some of them will be redirected away from the interface if it gets entrained into the secondary flow. That was the idea. And that length scale HW happens to be h over 5. So what we're conjecturing is that if your particles are small enough to be entrained into this basically recirculating flow, maybe you have a chance of getting gradual accumulation. But if your particle is too big, I don't think there's any shot at this. If anything, I imagine the particles will really suppress this effect of fountain flow in the first place, so you would get this sharp accumulation. So this length scale is h over 5. So if you just put it all together, it does amount to h over d is equal to 5. So I was very skeptical of this. It was, first of all, too good to be true. And of course, the scaling is very simple. And another thing that you have to remember is you always have to be skeptical, especially of your own results. And earlier when I showed you the band fingering versus weak fingering, you also have to remember that I was switching particles. I said, one is small particles, the other is large particles. But if this scaling is really true, we should be able to see this without switching particle diameter. So that's what we did. So this is a small particle, and we're just keeping everything at 30%, and all we're doing is gradually changing h. So what we really see is that when you just go from, so there's a lot of information here. I just want you to focus on these two experiments, right below and above h over d is equal to 5. So here, this is what we call band fingering, and this is what we call weak fingering. Qualitatively, you can see it. But if it's really true, we should also be able to see the signature of band fingering we mentioned before. So if we measure lambda, which is basically the interfacial deformation, we said if you have band fingering, we should see a peak. So you see that right here, that's the dot. And if you have weak fingering, you don't see this, so that's a triangle, and lambda, corresponding lambda plot is down here. So just by changing h by 0.2 millimeter, we really see the difference. So I do think maybe there is something with the scaling that we're capturing right. All right. So again, key is accumulation. So we understand some things now. So we basically said as long as you have particle accumulation, you have recipe for viscous fingering because you have unstable viscosity gradient. And another great thing that we found is that for any of this to happen, we basically need to satisfy this condition. We need particles to be moving ever slightly faster than the mixture so that you get accumulation. Without this, nothing new that you do will actually result in this. And this is another food for thought. So if you want to do an experiment that's slightly different, that you know will change shear-induced migration, then maybe you'll see something different. So for those of you who are interested in experiments, I think that there's a lot of room for maybe trying out different things here. But anyway, so going back to beta, so we decided to call this velocity ratio beta, and this needs to be greater than 1. So we call this basically the bare minimum condition for fingering. We're not saying it's sufficient, but this absolutely needs to be met before anything interesting happens. And another great thing is that this condition needs to be satisfied basically far away from the interface. That's when particles need to be moving faster so they catches up to the interface. So we can actually do some analysis now because upstream away from the interface is when things are a little bit easier to deal with. So that's what we're going to do. We're going to try to actually resolve or calculate this beta maybe in two different limits. So depending on the time, I'll get to the other. So one is a continuum limit. So I've been sharing with you the experiments that's h over d greater than 10, about 10. So I know pushing it a little bit for calling it continuum, but if you let me, I will call it continuum. And the other limit is where h over d is maybe approaching 1 so that there can only be one particle between two plates, and there's a lot of room that we can play within that limit as well. So this is how we've been thinking about it anyway. And really, this is where numericist needs to jump in this limit right here when you transition from continuum to monolayer. I think there's a lot of interesting physics that happens in between. So let's start with this. So we decided to use suspension balance model, which is basically, sorry, I'm a little bit embarrassed. I don't know, because John Brady is sitting in the room, so I'm not going to make eye contact. Which is basically, because I'm going to say something that's probably not true, so maybe. Oh, really? Where? Oh, no. That's terrible. Please look away. So which is basically capturing the low Reynolds hydrodynamics of particle suspension as a continuum. And this is as far as my understanding. So really do correct me if I'm wrong, because every time I've given a talk, I've said this. So I've said it wrong many times, if then. So we basically are doing conservation of mass and momentum of the mixture coupled with conservation of mass and momentum of the particle phase. And the way you bring it all together is by looking at maybe these total stresses. And one thing that I just want to point out, and maybe you guys can tell me if it's wrong, is that what this model can capture is basically the particle normal stress, which is proportional to the gradient of shear rate. Does that sound okay? Right? And I think that's actually the key, because this is actually where the effect of shear-induced migration will come in as well. So we take this model, we use some empirical relationship for shear viscosity and normal viscosity. There are a lot. And we just decided to say, well, let me just take lubrication approximation. And we already said, I'm looking at a limit where I'm far away from the interface, that I'm going to treat this as a quasi-1D problem, quasi-fully developed problem. And that really simplifies a lot of the things, right? So we're going to take axisymmetric quasi-1D, and then you just get this coupled nonlinear ODE that we can actually we can solve using MATLAB. So that's what we did. So everything has been non-dimensionalized, but I'm just going to get to the result because this result by itself is not new. A lot of people have plotted this. I'm sure in other papers you can find the similar plot. So basically, this is a plot of particle concentration as a function of z. Wait, what is a z? The direction variable in the normal direction. Sorry, I'm like not forgetting words. I'm jet-lagged, so that's okay, right? Like I said, as you might expect, there is a higher concentration toward the center. That's where, due to the effect of shear-induced migration, so you can see the effect right here. And you can also plot the corresponding mixture velocity. And you can see for low concentration, you should basically recover the parabolic flow profile. Higher and higher concentration, you see more blunted tip, and that's what you would expect because there are more particles at the center. So all of this makes sense, and like I said, this by itself is not new. But the reason why we wanted to solve this is now because we wanted to solve beta, compute beta. So just to remind you, velocity ratio beta, you could just write it out this way, right? And we basically have everything from the previous slide to be able to plot it. So I want to mention a couple of things. This plot is very unsatisfying, and I'm going to tell you why. But let me at least clarify one thing. So you see that beta is actually decreasing with phi naught. And at first, we thought that's kind of strange. Why would it do that? But then we remember this velocity profile. So the higher the velocity, higher the concentration, more and more the tip gets. So in some ways, looking at this picture, it makes sense that the velocity ratio would go down as concentration goes up because of the way this velocity looks. Okay, that's one. Another thing I want to mention is that if you just use basically the injection constraint, so where this is the amount of particle we are putting in at the given volume rate, we can actually rewrite this expression and turn it into something extremely simple. So it's a simple math. So phi naught is divided by depth average particle concentration upstream. So this is a quantity that we can actually measure. I don't know if you remember, but we were able to measure it using image intensity data. So that means we can compare experiments and theory. So it's not great, okay, first of all. It does a little bit better at higher concentration, but it's really all over the place for low concentration, and the experimental data is for different values of H. Another thing is that whether it matches or not, there's another troubling thing. What is a troubling thing? So I said, for any of this accumulation to happen, for any of this fingering to happen, the minimum condition we need is that beta needs to be greater than 1. And look at the plot. Basically, it says beta is greater than 1 all the time. So in theory, you should see viscous fingering in all the experiments. At least we're meeting the bare minimum conditions. So basically what I realized is that maybe this beta is not the best way to go about it, because at least our measurement and maybe also the model does not work very well for low phi naught. So we cannot actually see the transition from beta that's less than 1 to greater than 1. That's what I was hoping to see. But in the process of doing this, we uncovered another thing that was actually more mystifying. If you actually look at the experiments carefully, so these are a series of experiments for H is equal to 1.4 millimeter. And we process the images so that we can actually really see the particle accumulation. The thing is, you can actually see evidence of particle accumulation for pretty low concentration. So this is 11%, especially 14, 20%. You can clearly see this ring formation on the interface. But we don't see observed miscible fingering till later on. So the question is, why this lag? Why doesn't particle accumulation lead to miscible fingering? So now I'm trying to ask a different question. Before it was all about how do we get fingering, how do we get fingering? So now the question is, why do we not get fingering when there is particle accumulation? So for us to be able to answer this question, the follow-up question is basically, what is stabilizing this? So if there was any time, I was going to talk about that a little bit. Do I have a little bit of time? Okay, so I'll just get to the point. So we did some analysis. So to answer the question, we actually had to jump back to the band fingering limit, where we're basically going to assume that H over D is such that there is only one particle per gap, and I know this is an approximation, but this allows us to actually come up with a pretty simple scaling law for beta. And the key point is that now the velocity ratio should be independent of phi naught and only a function of D over H. And actually that works pretty well with our experiments. So we now know for a small H over D limit, we know how particles move faster than the average velocity. We know that. Once you know that, now you can basically draw a very simple control volume. And this is really what we do in undergrad, right? Maybe even before then, for some of you, I don't know. I was educated in the US, so that's my reference frame. So you just draw a control volume around this band, and you can basically say, I know how much faster these particles are moving upstream. I know how this band must be expanding with an expanding radius. So can I just figure out how fast the volume of this band is changing? So simple mass conservation basically tells us how to calculate basically the volume of the band at any given time, as long as we know the initial condition, right? So that's not something we can always control. And it works really well with our experiments. And the only thing that we assumed here is that I'm going to assume inside the band, the concentration is uniform just to make my life easier. And what's nice about this plot is that now I can read off what this concentration needs to be to satisfy this mass conservation. It's 0.5. So the only thing I'm trying to get to here is that for band fingering, we have this very simplistic picture of what's going on. We have basically, think of it as two different fluids with two different viscosities with a sharp jump between the viscosities that's set by these concentrations. And we know how this inner surface R1 is growing relative to R2, which is the outer surface. And the question is, can we actually understand what sets this unstable wavelength, wave number? And we decided to think maybe the answer is right here. And I know the concentration inside the band is really high. It probably acts more like a non-Newtonian fluid, and there's a lot of complexities here, but maybe we can try this simple idea that we can use surface tension, or the fact that we have this outer surface that wants to be stable, and we have this inner surface that wants to be unstable. So if we couple those two together, maybe we're going to get the right wave number. So that's what we try to do. And you can kind of see the evidence of this when you basically go back to our experiments and look at how the interfacial deformation changes with time. It peaks when there's a band, and then it actually tries to recover the circular shape, so it tries to recover. Okay? So that's what we did with the linear stability, and it's really similar to what Cardoso and colleagues did back in 1995. So I'm not going to go into the detail, but I know it's very straightforward. Blah, blah, blah. And the result, so maybe the only thing I'm going to say is that the way that we find the critical N is by computing the amplitude of perturbation, eta over time. And whichever amplitude has the highest value at the critical time is what we're calling the critical N. So we're not looking for the mode with the fastest growth rate because everything is time dependent. We're actually integrating the amplitude over time. That's the only thing I wanted to say. And we also do not empirically fit critical time. We basically look for critical time at which the inner perturbation grows to be the particle band size. After all that, it works okay with the experiment. So this is our experimental data. This is our theory for different phi naught for different h. So surface tension seems to be doing okay. So just to summarize, okay. So we basically learned two things, I hope, that if you have particles, non-Brownian particles that undergo shear-induced migration, then you are going to have particle accumulation on the interface. And that particle accumulation will give you destabilizing viscosity gradient, and you can get fingering. So you learned that. And we also learned that maybe the surface tension on the outer interface is what stabilizes the system. That's why you don't see this fingering all the time, even when you have particle accumulation. But what we recently found is that maybe that's not enough. So here we decided to just look at experiments where, so there's no outer interface. Okay, so we just have particle suspension between inside the Hilly-Shot cell, and we're going to inject oil. So this is a particle with oil mixture, and we're going to inject pure oil. So we are doing everything completely miscible with a 10% concentration. At least as far as I'm concerned, I don't see any miscible fingering. And another argument you can make is that maybe the wavelength is so small that maybe it doesn't look like fingering, and you are right, maybe there is something like that. But what's been interesting has been there has been a literature the last couple of decades, I guess, already. Oh my God, 2018, right? It's time, right? That basically says you are not going to get miscible fingering unless you exert some critical mobility ratio, even without the stabilizing surface tension. And we believe that there is some tie to this in our experiments. So this is with a 35% that's actually above this critical mobility ratio. We definitely see fingering. Another thing they found out by reading this literature is that this viscous fingering or this critical mobility ratio has a lot to do with what happens in the z direction. In our system, we can really change what happens in the z direction by changing h over d. So same concentration, changing h over d, you get different fingering behavior. I think I went over time, right? All right, so great. So that's it, actually. So let me just end with you two things that we're doing in lab since then. So this is one of the things that we're working on. We're kind of excited. We're just about to understand something new, I think. I don't know, maybe not new. Maybe somebody did it 10 years ago. So, but we don't know that yet, so that's exciting. So that's miscible fingering. Another thing that we're looking at right now is actually how particles behave near a receding interface in a very high confined channel. So that's something that we think we understand, but I don't have time to get into it. The last thing I want to mention is that early on I said, without shear-induced migration that allows particles to accumulate on the interface, you are not going to see anything interesting. Or if you change something in your experiment that's going to change shear-induced migration, you are going to change the fingering behavior. Everything is tied together. So that made a lot of sense. So we basically just decided to put in bi-dispersed suspension, different sizes, and we already know that large particles, time is up, accumulate faster near the center line. So they reach, large particles are red, they reach the interface faster and they affect fingering more, and that's all the time I have. So thank you so much for your attention. Thank you. So I can stop now, right? No time for questions.
No, there are 5 minutes. You said you wanted done.
Oh, no, okay, good, okay, good.
And the audience is fascinated by your presentation and has lots of interesting questions to ask. Who would like to go first?
Oh, no.
Yeah, so you showed about the U-turn that the fluid makes near the interface in that frame of reference.
Yes.
So suppose you put very tiny particles, do you see that happening?
Yeah, actually, even with the relatively, these are not tiny particles, but the 100 micron particles that we have, if we actually watch the movie very carefully near the interface, you can actually see these particles come towards and then basically bounce back. So we can actually see the effect of fountain flow, even with our particle sizes. Yeah.
Is it on? Yeah. My question is, if you run your experiment for a very long time, basically you have the onset of fingering, then you have these lobes that actually grow over time again. Could you get sub-fingering again? And if you wait a long time, could it almost be a straight interface, that you lose the radial component?
Yeah, that's a really good question. Right, because it's kind of shedding off more particles as it's forming clusters.
Yeah. If you just continue the inflow, does it break up in like a second stage process?
Yeah. Because I see that even with the initial, with our experiments that we're doing, we definitely see secondary lobes forming again, and then eventually, if I had if we had a really, really large cell, we might actually uncover.
Yeah. Of course, you may run out of laboratory.
Right, exactly. Maybe you can do it in a rectangular cell. Yeah.
Hi.
Oh, sorry. Oh no, that's you. Okay, sorry. Can I get that question? I was kidding. What did I get the math
This
wrong?
is a simple question.
Okay.
So the idea is that at the interface where the particles are collecting, you would expect the surface tension to rise because the curvature of the interface is increasing because of the presence of the particles. I would think that would be a stabilizing influence.
Right. Actually, a lot of people look at that, right? And my understanding is that because in the experiments where they see particles helping to modify the interface, the particles are actually de-wet or absorbent the interface, so that what you're getting is this particle-laden interface. I don't think we have that in these experiments. The particles are still completely wetted by the oil, so I don't see any evidence of particles actually crystallizing or absorbing on the interface. Actually, we really try to get that. I thought it would be fascinating if we could actually jam it enough that in the end we would rigidify it completely, and maybe because it's always expanding radially, we were never able to see that. But yeah, that's an interesting point.
So for the other limit, when you think of these as just Brownian particles, would there not be an accumulation because there'll be a ridge formation because of how it spreads?
Oh, you mean, can I see this with the colloidal particles?
Yeah, so once that, if there is an accumulation in the Brownian case, then the argument of it being an unstable viscosity gradient continues to apply there too.
Yeah, exactly. No, I totally agree. So yeah, if you can actually do it in colloidal particles, I would love to see it. Actually, because one thing is, I was also wondering, even with, so in theory, shear-induced migration is supposed to be for non-Brownian particles, but I was also thinking that, but what if you have colloidal particles that are governed by Brownian motion, but you have really high channel confinement? Would that help focus particles near the center line, and would they actually accumulate on the interface? So I think as long as particles accumulate the interface, big or small, the same mechanism should work, I think, yeah.
It begins to look like a granular medium, and it's known that there's a viscous fingering instability, Poulican. I've not studied it in detail, but I'm wondering if you couldn't have some kind of fingering like that, which doesn't depend too much on the fluid.
Could you remind me what you mean by the granular media and what kind of fingering?
Advancing interfaces in granular media are unstable.
Right, you mean like on an incline,
Poulican,
right?
Yeah, usually
right.
it's not between gap, it's not in a gap. It's usually
Right,
down.
right, yeah.
And I'm wondering if it's related to the granular. Maybe somebody knows.
Yeah, so that's very similar to what Andrea Bertozzi did on an incline. So that's why she did particle laden flows out an incline. And actually what she showed was that in the limit of high concentration particles that rises to the top due to shear-induced migration, they collect at the moving interface, and it actually helps suppress fingering.
So it may not, it might be suppressed by the existence of the upper plate.
Oh no, so Andrea Bertozzi's experiments was without the top, so it was a free surface film, yeah, so, but maybe if you have enough particles, maybe there'll be another regime where it acts really more like dry granular media and it will still finger, but yeah, I'm not sure.
My understanding was that Poulican's experiment was dry, but involved a mixture of two sizes.
Okay, the particle segregation, right? Yeah.
So it might be that each particle phase had its own viscosity.
Right. Maybe correction, or Natalie has correction.
Some regular fingering experiments that I did in my lab, in my presentation on Wednesday.
Oh, great.
Follow up on that later.
Great.
Well, I think we should draw that to a close, except could I just ask one question?
Sure.
And it's almost the exact opposite to what you've been saying, which is how particles might destabilize a spreading Newtonian fluid.
Yes.
The inverse would be, is it possible to get particles to stabilize a spreading non-Newtonian fluid? Because it's non-Newtonian, it can be unstable, and particles somehow might be able to stabilize it.
Sure. I don't know. The answer is maybe. I don't know. You mean suspended particles in a non-Newtonian fluid? Yeah, I don't know. Yeah, that's a great question.
Well, I think, Ishan, if the answer is I don't know, you have to run this conference again and invite Sungyon back again so that we can find out the answer. But ladies and gentlemen, let's thank Sungyon for really a wonderful presentation.